Hello mathematicians, we're now going to have a look at paying off a loan. And long-term loans, particularly housing loans, but I guess some more expensive cars, boats, even land loans, are usually paid off by regular instalments, but the compound interest which is charged on the balance which is owed at a particular time. So unlike some personal loans where you keep getting charged interest on the amount that you borrowed, this one takes account of the fact that you've paid some money back, so the interest amount keeps reducing. Of course, the loan's finally paid off when the amount owing is zero. So that will actually, while it seems trivial, that will become important in our proof. So what we do is to build up a pattern. We're all about sequences and series here. So to find the amount A sub n owing after n units of time, we do this sort of thing. We find what the principal earning compound interest would amount to if no instalments were paid. So if this money was borrowed and it was just sitting in the bank earning compound interest, what would it amount to if no instalments were paid? Now, we don't consciously do this, but it's an important point in interpreting the formula, because this is what the money would be worth to the bank. So we have to at least give the bank the equivalent of what they could get by putting their money somewhere else. What we then do is to find what each instalment will amount to as it earns compound interest. And again, we don't think of it necessarily as that, but that's what we're doing. We're going to imagine if we made a repayment, what it would earn as compound interest, and that becomes something in our favour. The amount owing after n units of time is obviously the principal plus the interest minus the instalments plus their interest. And the loan is paid off, as we said, when you don't owe any money anymore. Now, keep those points in mind, although you may never consciously think about them while we're setting up the pattern. And in fact, this is probably the key phrase for you in terms of doing a calculation. We're going to be searching for the sum of a GP. So let's look at this problem. Ali takes out a loan of $10,000 to buy a car. So this is the principal. He'll repay the loan in 5 years of 60 equal monthly instalments, beginning 1 month after he takes out the loan. Interest is charged at 6% per annum, compounded monthly, so we know that that will reduce to 0.5% per month. And we want to find out how much the monthly instalment should be for all those conditions we spoke about on the previous page to be obeyed. So we start to set up a pattern. So this is the amount owing at the end of the first month. So our $10,000 that we borrowed will attract interest, 1.05, and then we'll make a repayment. That then becomes the balance at the start of the second month, so that attracts interest, and then we make a repayment. Now, when we rewrite it like this, so we're only necessarily rewriting it like this so that we can start to look at the pattern to get the sum of a GP. But this is where there's another interpretation. So this little bit here, keep wanting to charge him a lot for this car, 10,000 multiplied by 1.05 squared is what the bank could have got for its $10,000 if it invested it. This little bit here is not only our number of repayments, which is 1, 2, but it's the interest on the first repayment that we made, because we've given one repayment to the bank and it has been earning interest, or it could have been earning interest if we'd kept it in our account. So we're going to subtract from the amount owing this GP. Now, as I said, you may not want to, or you may not need to think of it like that, but sometimes it just helps you interpret the data. Now, after 60 months, so when the loan is going to be repaid, the $10,000 gets multiplied by 1.05 to the 60. But again, if we just look at the pattern, here was a 2, here was a 2. Minus R outside of, and we've got all of these things here, so I'm just writing it in reverse order. This represents our first repayment, which has been effectively attracting interest for 59 months, 59 periods. So what this represents in here is the sum of a GP with 60 terms. So again, if you're trying to think about patterns, remember this number here was 1 when this number was 2. So it's always 1 less than this one here. So this GP has actually 60 terms. A is 1, R is 1.05. So if we then make use of the fact that after 60 repayments our balance is 0, then we're just solving this equation here. But interestingly again, when you solve this equation, you may choose to think of it as the fact that on this side, here's the money that the bank could have earned by investing its own money in another bank. Here is the money we've given the bank, the repayments and all of the interest that we should have earned on that money. And then we solve it. That's all there is. So when you put that into your calculator, $193.32. Now there's a final check to see whether your answer makes sense or not, which is to take your $193.32, multiply it by 60, the number of payments. It's got to obviously amount to more than 10,000, and sometimes it will amount to significantly more than what you borrowed, because we are having large amounts of money for long periods of time. So it's all about patterns, as I said. We're aiming to set up the sum of a GP somewhere. So let's look at this one. Natasha and Richard take out a loan of $200,000 on 1st of January 2002. There are monthly instalments of $2,200, so this time they're telling us the repayment. Interest is 12% per annum compounded monthly, so that means 1% per month. So first part, find a formula for the amount owing at the end of n months. This is the crucial step, setting up a pattern. So at the end of the first month, I've used A, should have been O, but it doesn't really matter. So 200,000 will have attracted interest for 1 month, and then we're going to make a repayment. For the end of the second month, our balance at the end of the first month is going to attract interest, then we'll make a repayment. But at this stage, if we rearrange that, and this is the bit which often is tricky, I guess, if you're not remembering that you're after a sum of a GP, we've taken out our $2,200 as a common factor, our negative $2,200, and it's left us with 1 from this term and 1.01 from this term, so we can see the beginnings of our GP. And again, for what it's worth, this is what the bank could have earned, this is what we could have earned, and we've given it to the bank. So we can see the pattern after this amount of time, I think. So after n months, the 200,000 will have earned, attracted n lots of compound interest. We've made n repayments, and the one that's been in there the longest has attracted n minus 1 lots of compound interest. So once we have this pattern, then we're really set. So how much is owing after 5 years? Before we jump on there, all I've done here is that I've actually taken this sum of the GP and I've written it as the formula for the sum of a GP. So over the page, how much is owing after 5 years? We just substitute n equals 5 into that. And we see that we owe nearly 199,000. So 5 years down the track, we owe almost what we borrowed. But the thing about reducing balance loans is that they reduce the balance, the principal, really slowly to start with, but then much more rapidly as time goes on. So how long does it take to repay the full loan? So we said when n equals 0, the loan is repaid. So put n equals 0 in there. Solve our equation. I'm not sure what happened to the bottom of that. I've multiplied through by 0.01. So each term has been multiplied by 0.01. So that's gotten rid of that fraction, and it's reduced that 200,000 to 2,000. So it's just to make the numbers simpler, no more than that. it's not necessary. So then we solve this equation, and we're after n, so we're going to need logs. So if we divide through by the 200, so that we've done that, take the log of both sides and then use our power rule, we get to that, and that comes out to be 11. So while it took us, after 5 years we'd hardly paid any, then to repay the full loan only took 11 years. 241 months. Sorry, 241 months. Sorry. So 11 was this thing here, obviously. I should make the recordings straight after I solve them, not a day or two later. So 241 months. Now, part C. How long does it take to... So, if we're going to repay half the loan, so here I have just copied the part for repaying the full loan, and if I'm going to repay half the loan, then the balance is going to be AN on 2 when I've repaid half the loan. So this part here is only 100,000, or 100,000 left to pay. And if I go through the same process of solving the equation then, so multiply through by 0.01, shuffle that $1,000 over to the side, which is different because that was 0 previously. Go ahead and solve this now, and that's not going to be 11, that's going to be 6, and I'll get 180 months. So it took 180 months to repay half the loan, but the full loan was paid off in 241 months. So as I said, the graph, if we actually graphed the balance of the loan over time, it would go like this. It drops off really rapidly at the end. And why would instalments of $1,900 per month never repay the loan? Well, $1,900 per month would never repay the loan because we can see that the interest on the loan is more than $1,900 per month. So we're never even going to pay the interest, so we'll never start reducing the principal. So, evens in 7D. Now these are long, tedious, but important questions because there's either one of these or a superannuation on every HSC over the last, I don't know what number of years. So you need to think about what the big idea is for this stuff, and I think it's all to do with interpretation and setting up the GP, but it's what you think which is the important thing.